Modern engineering can launch satellites into orbit, map the human genome, and simulate entire cities before a single brick is laid. We can 3D print organs, split atoms, and manipulate matter at the nanoscale. And yet, there are objects buried in sand, locked in museums, or still standing in silence across the world that we cannot fully reproduce today. These are not myths, not legends, not speculative tales passed down through folklore. They are measurable, testable artifacts and structures, built with tools that, by our understanding, should not have been sufficient to create them with such precision, durability, or complexity. In some cases, we can explain how they might have been made, but not replicate the exact material properties. In others, we understand the design, but not the process that achieved such refinement. And in a few rare instances, we still debate the fundamental engineering principles behind them. This is not about romanticizing the past. It is about confronting a reality that challenges our assumptions. Technological progress is not always linear. Knowledge can be lost. Techniques can disappear. Entire engineering traditions can vanish without leaving blueprints behind. Today, we explore 10 ancient technologies that modern science still struggles to recreate, not because we lack intelligence, but because something about how they were made remains just beyond our reach. There is a persistent assumption in modern culture that we stand at the absolute peak of technological sophistication. In many ways, we do. Our computational power, material science, and engineering capabilities far exceed anything available in antiquity. But capability does not always equal replication. This documentary examines ancient technologies that continue to challenge modern engineers, physicists, metallurgists, and historians. These are not fringe claims or conspiratorial artifacts. They are real structures, materials, and mechanisms studied by universities, laboratories, and research institutions around the world. As we move through these examples, the goal is not to suggest that ancient civilizations possessed futuristic devices or unknown super science. Instead, we will examine where modern understanding reaches a boundary, where we can analyze, measure, and hypothesize, yet still cannot fully reproduce the original results under the same conditions. If you value detailed explorations like this, where science meets historical mystery, consider subscribing. A like supports deeper research-driven content. And in the comments, share where you're watching from, your country and city. These technologies span continents, and it's fitting to know how far this conversation travels. Let's begin with engineering, stone, weight, and precision that defy expectation. The Great Pyramid of Giza remains one of the most rigorously studied structures in engineering history. Constructed from approximately 2.3 million limestone and granite blocks, many weighing several tons, it exhibits an alignment to true north, with a deviation of only about 0.05 degrees. This level of precision rivals modern surveying capabilities. Modern instruments can confirm this accuracy within seconds. But replicating such cardinal alignment using only Bronze Age tools without steel, GPS, lasers, or digital leveling systems remains experimentally unproven at full scale. The challenge is not theoretical geometry, it is field execution. Quarrying and transporting millions of blocks is itself an immense logistical problem. Positioning them with consistent precision over decades of construction requires coordination systems that we can hypothesize, but have not demonstrated at comparable scale under ancient constraints. Ramp theories exist. Spiral ramps, straight ramps, internal ramps, yet none have been conclusively reconstructed at full height in a way that resolves all structural and material challenges. The pyramid exists. Its precision is measurable. What remains uncertain is how such astronomical alignment was operationalized without instruments we consider indispensable. In modern-day Lebanon, the Roman site of Baalbek contains 3 limestone blocks known as the Trilithon. Each weighs between 800 and 1,000 tons. These are among the largest stone blocks ever incorporated into an ancient structure. Moving such mass even today requires multi-axle, heavy-lift cranes and reinforced transport systems. Yet these stones were quarried, transported from a nearby site, and placed with structural precision atop a massive platform. The quarry's proximity reduces distance, but not difficulty. The real engineering question lies in controlled lifting and placement. Positioning a 1,000-ton block requires precise load distribution and stabilization. A miscalculation would result in catastrophic failure. We can model plausible methods involving rollers, sledges, and inclined planes. We can simulate traction forces and friction coefficients. What we cannot do is experimentally validate an ancient method at full weight and scale using period-accurate tools. The issue is not disbelief in ancient capability, it is the absence of verified replication. Between roughly 300 and 1700 CE, Middle Eastern swordsmiths produced blades known for their distinctive wavy patterns and exceptional mechanical properties. These were forged from Wootz crucible steel, originally produced in India and Sri Lanka. Modern metallurgical analysis reveals nanostructured carbide formations within authentic Damascus blades. These microstructures contributed to a combination of hardness, flexibility, and edge retention that was remarkable for its time. Today, metallurgists can create high-performance alloys far superior by modern metrics. However, reproducing the exact historical microstructure found in surviving Damascus blades using comparable materials and processes has proven inconsistent. Ancient blacksmiths did not possess microscopes or spectrometers. Their process was empirical, passed through generations. Subtle variations in ore composition, temperature cycling, and forging technique likely contributed to the outcome. At some point in the 18th century, the precise method disappeared. Trade routes shifted, ore sources changed, and the metallurgical tradition faded. We can approximate, but authentic replication remains elusive. Roman engineers developed a concrete mixture using volcanic ash, lime, and seawater that demonstrates extraordinary longevity, particularly in marine environments. Modern concrete typically degrades when exposed to saltwater. Roman marine concrete, however, undergoes a chemical process that strengthens it over time. When cracks form, seawater interacts with lime clasts, generating aluminous tobermorite crystals that reinforce the structure. We now understand the chemistry. Laboratory recreations confirm the reaction. Yet large-scale industrial concrete production does not adopt this formula, largely due to cost, material sourcing, and production speed priorities. Structures such as the Pantheon have endured for nearly 2,000 years. The technology was not accidental. It was intentional material science. The formula was not lost entirely. It was deprioritized. Recovered from a shipwreck off the coast of Greece, the Antikythera Mechanism dates to around 100 BCE. It consists of more than 30 interlocking bronze gears capable of predicting astronomical events, including eclipses and planetary cycles. X-ray imaging reveals gear teeth of remarkable precision for the era. The device functions as a mechanical analog computer. Reconstruction today requires advanced scanning technology and precision machining tools. What remains debated is how ancient engineers achieved such gear accuracy without precision lathes or modern calibration instruments. No workshop has been found. No instruction manual survives. The device appears fully formed in the archaeological record, then disappears for centuries. Its existence suggests a level of mechanical sophistication not widely associated with its time. In sites such as Sacsayhuaman and Machu Picchu, massive stones are cut into irregular polygonal shapes and fitted together without mortar. The joints are so precise that a thin blade cannot pass between them. The walls are earthquake-resistant. During seismic events, the stones shift slightly and settle back into place. The Inca lacked iron tools and did not use the wheel for transport. Yet they achieved adaptive stone shaping for each individual block. Modern builders can replicate the visual style using diamond saws and laser guides. But reproducing the same seamless interlocking using period tools would require immense labor and extraordinary skill. The technique represents mastery refined over generations, not an isolated innovation. Beginning in the 7th century, the Byzantine Empire deployed an incendiary weapon known as Greek fire. Descriptions indicate that it could ignite upon contact with water and was projected through siphon-based mechanisms during naval combat. The exact chemical composition was treated as a state secret. It was transmitted orally and never recorded in surviving technical texts. Modern chemists propose mixtures involving petroleum derivatives, sulfur, and quicklime. Experimental reconstructions produce similar effects, but authenticity cannot be confirmed. We possess advanced chemical knowledge today, yet the original formulation and deployment mechanics remain uncertain. The technology was not rediscovered, it vanished. A clay jar containing a copper cylinder and iron rod, dated to the Parthian period, has demonstrated the ability to generate a small electrical current when filled with acidic liquid. Modern replicas confirm approximately 1 volt of electricity. Was it used for electroplating, ritual, storage? The absence of contextual documentation prevents certainty. We can replicate its electrical output easily. What remains unclear is whether electricity was its intended purpose. The device raises questions about practical experimentation that may not align with surviving written records. The Maya tracked planetary movements, including the Venus cycle, with extraordinary precision. The Dresden Codex documents astronomical tables spanning long observational periods. Their calculations deviated by only fractions of a day over extended cycles. Achieved without telescopes, this required sustained naked-eye observation and mathematical refinement across generations. We can replicate the results today effortlessly. Replicating the centuries-long observational continuity without modern instruments would be far more demanding. The knowledge was sophisticated, much of it was destroyed during colonial disruptions. It was not disproven, it was erased. The Nabateans engineered an urban water management system in Petra, capable of capturing flash floods and sustaining a desert city. Channels, dams, ceramic pipes, and gradient-controlled flow systems were integrated into the landscape. Modern hydrologists acknowledge the sophistication of the design. We can construct superior hydraulic systems today using computational modeling. But replicating Petra's adaptation without digital tools would require extensive environmental iteration and observation. The system declined as trade networks shifted. The expertise faded alongside it. These 10 technologies do not suggest that ancient civilizations possessed hidden futuristic devices. They suggest something more complex and perhaps more unsettling. Knowledge is fragile. Techniques refined over generations can disappear within decades. Materials can outlast the understanding of how they were made. Engineering traditions can vanish without leaving instructions behind. Modern science continues to study, analyze, and reconstruct these achievements. And in doing so, it reveals a truth that challenges linear narratives of progress. Sometimes, what was once mastered must be rediscovered.